In the previous module, we have looked at the types of signals being classified based on the independent and dependent variables. The signal can also be classified on the basis of its symmetry. For example, consider the signals shown on the screen. This signal, let's say it is being defined from -1 to 1 as a function of time. Let this function of the signal be x of t. If you look at this signal, we may see that the signal is symmetric in nature, meaning the signal that is there on the left appears on the right exactly. This can be represented as x of t equals to x of minus t. What does that mean? X of t, that is the signal, is exactly equals to the signal on the other hand. And this is true for all the values of t. If this is the case, then such signals are called as even signals. So let me write that, even signal. Its discrete time equivalent can be written in the similar fashion as x of n equals to x of minus n, and that is should be true for all the values of n where n is an integer. Similarly, consider another signal. Being defined something like this. So it's similar signal but not the exact one. Now this signal here being defined from -1 to 1 as a function of time. If you look at this signal, you may see that the signal that is there on the left appears on the right but in negation. This can be represented mathematically as x of t equals to minus of x of minus t. You can see here that the signal that is there on one side appears on the other side but in negation. And if this is true for all the values of t, such signals are called as odd signals. Its discrete time equivalent can be represented in a similar fashion as x of n equals to minus of x of minus n, and this must be true for all the values of n. If that is the case, then it is called as an odd signal. Even an odd signal are having one special property. The property is any signal, say x of t, can be expressed as a summation of its even component xe of t and its odd component xo of t, where xe of t is being defined as x of t plus x of minus t by 2, whereas the odd component xo of t is defined as x of t minus x of minus t by 2. And you can clearly see that if we add both of this, will give you the original signal x of t. In a similar way, we can define the same as for discrete time case. So if we have x of n, any x of n, any discrete time signal can be expressed as a summation of its even component and its odd component, where the even component xe of n is defined as x of n plus x of minus n by 2, whereas the odd component xo of n is defined as x of n minus x of minus n by 2. Here also, if we add both of this, you will get back the original signal. Let's take an example to prove this. Consider this simple signal being defined, let's suppose, from 0 to 1, where the independent axis is time. Let's say this signal is x of t. Then in order to distribute, or in order to express this signal into its even and odd component, first we need to define x of minus t. And as we have seen, that x of minus t is simply a flipped version of this signal. So this appears to be something like this. If we simply flip this signal, this would look like this. Let's the amplitude be 1. So it is defined from minus 1 to 0. What is this? This is x of minus t. Now if we need to build the even component is simply adding x of t and x of minus t and further scaling it by a factor of half. So if we add both of these signals and scale it by a factor of half, the resultant signal will look something like this. So the resultant signal is xe of t that looks like this, where the amplitude is half, and this is xe of t, or the even component of the original signal. If we need to build the odd component, we need to go with the same procedure but with a negation. So the odd signal, let's say xo of t, is defined by subtracting these two. So x of t minus of x of minus t. So 1 minus 0 will give 1 on the right hand side, but 0 minus 1 will give minus 1 on the left hand side. And that 2 divided by 2 will give the resultant signal something like this. So the resultant signal will be like this. So this being half, this being minus half, centered at 0, and this is the odd component. And we can clearly observe from these two that if we add both of this component, you will get back the original signal. This is all about the even and the odd signals. Now consider the signals shown on the screen. Say the signal is, let's suppose I'm drawing some signals. The signal in the green, signal in the blue, or say signal in the yellow. Let's consider these three signals. Now, if I ask you a question that, tell me which one of this signal is larger than the rest, or is the largest among these three. Now, can we have a metric or a measure using which we can determine the largeness or the size of the signal? We may see that here, for example, this blue signal is having small duration but a larger height. Similarly, the green one is having smaller height but larger duration. Whereas this yellow one is having the height varying with respect to the time. In all of these different cases, can we have a metric that can determine or that can act as a metric for largeness or size of the signal? Well, the simplest possible case that we can think of is the area. If we look at the area of these three signals, these are different. So area, can it act as a metric for the size of the signal? Well, if we take the area of this signal, the area for the blue one may be some finite value, for the green one again maybe some value, but for the yellow one, which is a sinusoid, appears to be 0. Why? Because the area of the positive part is equals to the area of the negative part, so they both cancels each other. So although the signal may appear to be somewhat finite, the area gives 0. We don't want such metric. The metric should give or represent the largeness or the size of the signal in a finite value terms. So what could be an alternative? An alternative could be to have the mod of this signal and then calculate the area. Then the cancellation of positive and negative part, the problem won't be there. Or what you can do is simply square the signal. If you simply square the signal and then calculate the area, then again the problem would be solved. What was the problem in the area? The problem with the area was it was giving 0 values for such kind of symmetric signal. So either we can go for the mod or the square of the signal and then calculate the area. We will prefer the square as the metric for various reasons. So if we pick the metric as square of the original signal, so it is x square of t, and this metric is known as the energy of the signal. We square and then we take the area, so that is from minus infinite to infinite. Now if we have an energy, we can also define the power. So if we have energy being defined like this, the power can be defined as follows. So this energy can also be represented as infinite, this infinite over a duration t, where the t limit is approaching infinite, and this being x square of t dt. The power can be expressed as P equals to, now we know that if we have the energy, we can calculate the power as the average of this energy per unit time. So it's like integration over a period of t, x square of t dt divided by t, and then put the limit t tends to infinite. Now we can classify the signals based on what is called as an energy signal or a power signal. Let's take some examples. Example, let us take the simplest example of the signal shown on the screen. So let that signal be, say, 2, being defined between 0 to 1 as a function of t. So let this be x of t. If we try to calculate the energy or the power, we can do that using the formulas just specified. So the energy here would be integration from minus infinite to infinite x of t squared dt, that turns out to be 4. If we try to calculate the power, power turns out to be 0. Now in this case, we have the energy as a finite value and the power as 0. So let me write that. So energy is finite, whereas the power is 0. Let's take another example. Let's consider the same signal but not finite in duration. Instead, we'll take the same signal being starting from minus infinite and last till plus infinite. So it is everlasting signal with the amplitude being 2. Again a function of t. So let this be x of t. If we try to calculate the energy and the power, so the energy here, as we can see, the energy is defined as integration from minus infinite to infinite x square of t dt. This turns out to be infinite. Whereas the power, if we try to calculate the power, it turns out to be 4, because the power formula is limit t tends to infinite integration. Of course, before that we need to take the average integration from minus infinite to infinite, so that being represented as minus t to t, or over a period of t, x square of t dt. This turns out to be 4. So in this case, the energy is infinite, whereas the power is finite. So this is the second case. This is different from the previous one. In the previous case, we were having the energy as infinite where the power as 0, whereas in the second case we have the energy as infinite but the power as finite. Let's take one more case. Example. Let's say the example is like this. So the signal is simply x of t equals to t. If we try to calculate energy and power for this signal, the energy turns out to be infinite and also the power turns out to be infinite. So in both energy and power, if it turns out to be infinite, then this signal is neither an energy signal nor a power signal. So let's summarize all three examples. In the first example, let's make a table. In the first example, we have calculated both the energy and the power. We found that if energy is finite, so if it is finite but the power is 0, then such signals are called as energy signals. In the second case, we have seen that the energy is infinite but the power is finite. Such signals are called as power signals. And the last case that we have seen was the case of x of t equals to t, where both of the quantities, the energy and the power, was infinite. This is also infinite and the power is also infinite. Such signals are neither energy nor power signals. We shall see more into this in the next module. Thank you.